Hello students, how are you? After such a long gap in Corona gap, actually, I assume that all of us are aware of what are the safety precautions we need to take and all those things. We have seen all those videos, but the point of coming over here, appearing before you is this need not stop our intellectual effort of learning something. We are at the verge of completed. We have completed the first year and we are very eager to learn the new syllabus, NCERT syllabus I mean, and 12th, and without, in order not to stop that intellectual effort, we have decided that we'll go starting the regular teaching how we are doing from the very first chapter onwards we'll be starting, and let us see till what time we need to continue with this kind of format of a teaching. Fine. Okay, so as far as the syllabus is concerned, we are having 15 chapters in 12th, and of the first three chapters is electric charge and field, electric potential and capacitance, and current electricity. All this together we can call electricity. That broadly can be categorized into two parts: electricity and current electricity, static electricity and current electricity. As the name suggests, static electricity or electrostatics is the branch of study which deals with the effect of a charge at rest, and current electricity is all the study involving the effect of a charge in a motion. So we will be starting with the electric charge and field. Fine. So just to have a little background, what I always suggest you to not to jump into the depth before entering inside the introduction part or the basic, the background of it. Let's start it. Just to start with this introduction, I must take you to so very old of times. For example, let's say 500 or 600 BC before Christ. Then human beings, we were having a various kind of observations for which we didn't have any explanation. For example, whenever we try to touch something, we got a shock kind of thing. Or today also we can see from your common experience, suppose on a dry day you take a comb and you comb your dry hair with it, and you will see that it will be able to attract some bits of papers towards it. And if we are seeing we are observing this for the first time, we may be shocked, or we may be worried what is happening over here. Is it magic or something like that? And within some time it will lose its power to attract. It will not be able to attract anymore. But again, if we'll comb our dry hair with it, again the same phenomenon will be repeated. Again we can see that the comb will attract the bits of the papers. Fine. Similarly, if you take a glass rod and you rub it with the silk, the same attraction between the glass rod and the silk is taking place. So there are very many pairs like that in nature where this kind of effort is feasible, but we were not assured about the reason behind it, why it is happening. So the cause of it we were not aware of. Then there was the explanation. There were various explanations, but the explanation which was granted and accepted all over the world is there is a fundamental property of a matter which can be an explanation for these electromagnetic interactions. To say this, to explain these interactions between certain pairs, but later on we saw that these interactions are electromagnetic in nature. That's why we can say them to be electromagnetic interactions. So what's the cause of that? The property by virtue of which certain pairs of matter develop a kind of property to attract or repel each other. This electromagnetic interaction could be explained through a property called electric charge. or simply charge, which can be attractive or repulsive in nature. For example, we have a glass rod that is rubbed with a piece of silk, let us say. And similarly, we will be having another glass rod, and that is rubbed with another piece of a silk, let us say. Okay, then it is seen that after rubbing the glass rod with this silk piece and the glass rod with another silk piece, if we'll bring these two glass rods together, they repel each other. If we'll bring these silk rods together, they repel each other. If we bring the glass rod and a silk closure, they attract each other. And if we'll bring the glass rod with silk closure, they attract each other. This glass rod attracts this silk, this attracts with this. So what we concluded is, whenever the rubbing between two substances take place, one is glass, one is silk, then there is a repulsion between glass and glass and attraction between glass and the silk. What you can do in a day-to-day life is, in a dry hair, you comb with a comb, you just rub your dry hair, and after that you take the comb near bits of papers. Those papers will be attracted. So what is behind that? Then we came to the conclusion that there are two types of charges. Positive and negative. See, there are two types of charges. This is only one explanation of what we are seeing. This is only one observation of this is only explanation of the observation. Now, if we call one to be positive and the other to be negative, we took various pairs like this and we checked, and all these phenomena could be explained by this assumption. What we are saying is, whenever two pieces are rubbed against each other, one of the piece gains a particular kind of charge and the other piece gains some other kind of a charge, and these two charges attract each other. So let us say now, using these terminologies, one gains positive charge and other object which is rubbed against it gains negative charge. And whenever positive and negative are coming together, there is attraction between each other. And whenever the same like charges, negative are brought closer to each other, or positive are brought closer to each other, they repel. Fine, that is repulsion. So we can say, in short, attract or repel, but what amount of force? So the next step is quantitative in nature, which a scientist called Coulomb gave this, and that is very famous as Coulomb's law of electrostatics. Now, in your first year, we had studied the Newton's law of gravitation, right? I am giving that as that will serve as a background over here. I am just repeating. Let me take 1 minute in that. If two masses m1 and m2 are separated from each other where distance r, then the force of attraction between them is equal to g m1 m2 by r square. What Newton said is, the force of attraction between any two masses separated by a certain distance is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. So F is directly proportional to m1 m2 by r square, or F is equal to some constant of proportionality multiplied by m1 m2 by r square. That constant of proportionality was given a symbol G, which is universally the same. That's why it was called Newton's universal gravitational constant. So you remember this, right? In the same light, Coulomb's law. Similarly, whenever there are two charges separated by a distance r, then the force of attraction or repulsion between them is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Or we can say F is equal to some constant of proportionality multiplied by Q1 Q2 by R square. This some constant of proportionality is equal to 1 in CGS system and equal to 1 by 4 pi epsilon naught in MKS system or SI system, Standard International System. Okay. Now since this constant, this force is electrostatic force, so we are writing Fe, and this force was a gravitational force, so Fg, right? So Fe is equal to k q1 q2 by r square. Now k is equal to 1 in CGS system, so F is equal to simply q1 q2 by r square in CGS system. But that system we are not going to use many times. All the time, almost all the times we will be using SI system for units only. So safely we can write F is equal to 1 by 4 pi epsilon naught q1 q2 by r square. Now I am aware of the question what you are thinking of, what is epsilon, and that should be coming to your mind naturally. Now the thing is, see here, what was the constant of proportionality was fixed in the entire universe. You remember, that's why we call that universal gravitational constant. But in case of electricity, it depends on some factor. What is that factor? Suppose this is Q1, Q2, whenever we are taking, inside that, what is the medium? Suppose there is air. If it is air, there is this force is this one something, and instead of air, if oil is taken, or if two charges are kept inside kerosene or different mediums, if two charges are kept in different mediums, this force of attraction or repulsion between them differs. So this constant is not a universally gravitational constant, but that constant depends on the medium in which the charges are placed. Fine. Now it is seen that constant is always 1 by 4 pi times some property of the medium. So 1 by 4 pi remains same, and from where we are seeing this? From various experimentation. We took the same charge between different mediums we took and measured the force, and we came to the conclusion that whenever we do this, q1 q2 by r square is fine, and 1 by 4 pi also is coming all the time, but here only something that is varying all the time. And what is that something? That something is dependent on the property of the medium which is taken inside in between q1 and q2. Fine. And that effect for different material or different mediums is given a name permittivity. Okay, so permittivity of the medium can be anything, and the permittivity symbol is epsilon, this much only. Remember, here I took epsilon not epsilon. Epsilon is the permittivity, but if this medium is changed again and again, the permittivity also will change. But for the vacuum or for air merely, this is epsilon naught. Permittivity of vacuum is epsilon naught, and since almost all the experiments we will be doing in vacuum or in air only, and that is why we are safe to deal everything, all the numericals from the practical point of view, to take F is equal to 1 by 4 pi epsilon naught q1 q2 by r square. Fine. So depending on this much, we are going to do some numericals. But one more point I'll say here, that what is the force? It's a question for you. It's a scalar quantity or vector quantity? Good. Of course, it's a vector quantity, right? Now Coulomb's law, you understood? Now Coulomb's law, if we are going to represent it in a vector format, how should we write? See, F is equal to Q1 Q2 by R square, or to be more accurate, F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square, right? But F is a vector quantity, we know. So writing the same in vector form. So what I'll do, vector sign over the force F symbol is equal to 1 by 4 pi epsilon naught, then Q1 Q2 by, now the same thing I can multiply and divide so that the total remains same. R square, this much was there, now I multiply and divide by R. So R square into R, this became R cube, and this R I am writing as a vector. This is the vector format of Coulomb's law. Fine. Now if, what is this formula? It is one expression, mathematical expression, which governs the force of attraction or repulsion between two charges, and depending on this concept we are going to do some numericals. Now